Hi everyone, welcome back to Chem 40C. It's been a while. Sorry, I've been dealing with a lot of personal issues, and quantum mechanics is really difficult right now. Um, but yeah, here's chapter 20. So last time we learned about carboxylic acids, and I told you that their chemistry wasn't really interesting because you can't really do much with this carboxylic acid, right? It's important in a lot of drugs and a lot of um, amino acids and in our bodies. But in terms of organic chemistry, it's really not that interesting. You only have this acidic H here, which you can depronate, but it makes a carboxylate, and we know from last time that it's really stable. So that's why we have a lot of these derivatives or things that we can make from a carboxylic acid. So first off, we have this acyl chloride, right? Acyl chloride. This can be any halogen. We usually use chloride or bromide. We have anhydrides. As you can see, it's like two esters sort of, but this is a carbonyl at the end. We have, of course, esters as we know, and then the least reactive out of all of them, amides, right? So chapter 20 really goes in depth about all these derivatives here and their chemistry and how you can synthesize them. But in this video, we're going to be focusing on the two most reactive one. We're going to be focusing on the acyl chloride as well as the anhydride, right? So let's get started. So first, we're going to focus on the acyl chloride. As you can see, I have that over here, acyl chloride. So again, these are carbonyl carboxylic acid derivatives, which means you can make them and synthesize them from carboxylic acids, right? Which is what we have over here. So this is a pretty easy reaction, right? We can just do this chlorine attacks to a double bond here because of that strongly positive. You all should know this by now. This is pretty easy, right? And then this Cl is now bonded. And just to remind you what our acyl chloride looks like, it looks like this, the double bond O and then the Cl. So in this case, we just need this oxygen to make this double bond over here and this OH to leave, right? But that's not what's gonna happen. Which one is a better leaving group? Is it gonna be this hydroxyl or this chlorine? It's actually gonna be this chlorine, which means that even though this reaction it can proceed, it's not going to proceed because chlorine is a better leaving group. So if you want to draw the arrows for this reaction, it's an equilibrium. So there's a lot of, the arrows will go pointing towards the beginning product, right? So how can we defeat that? Well, we use a different type of reagent. In this case, we can use a thionyl chloride, this thing over here with the sulfur group in the middle, and then the oxygen, and then two chlorines at the end. This is a really weird mechanism, but stick with me. We can go through this together, right? So first off, I wanted to just focus on this thionyl chloride over here. The one thing that's standing out to me about this compound is there's a very large delta positive on this sulfur, right? You can see it's bonded to two chlorines, which are one of the most electronegative elements, right? So it's going to have a delta negative here. And it's also being pulled by the oxygen. Although oxygen compared to chlorine is not as electronegative, it's still being pulled, right? So this is a delta negative as well. So now if there's a lot of delta negatives on these, that means this sulfur has a huge delta positive, right? And because it has this big delta positive, we can attack it with one of the oxygens that we have here. We can do this oxygen here, we can, but we also had to remember that this lone pair here, these lone pairs are involved in resonance. So it's probably not going to attack. And also it's really stable here. And we're actually gonna attack it with the carbonyl oxygen. So if we do that, we attack the sulfur and then this double bond goes up, right? Again, this is a really weird mechanism and don't worry too much, just try your best to follow along. So we have this compound now, O and then Cl and then Cl. if we do our formal charges, let me move this down here. Sorry, I never know how much room to leave for me. So if we do our formal charges, this oxygen over here has a positive charge, and this one has a negative charge, right? Now this is where the weirdness comes out. This oxygen at the top right here is gonna get that double bond back, and then one of the chlorines will leave, forming us this product over here. O with the S, double bonded to O, and then we just have a single chlorine, and then now a chlorine as our leaving group, right? And then there's still this positive charge on this oxygen, right? And then you can do some resonance with the structure over here, right? If the lone pairs on this oxygen comes up, it goes up like that. You can do that, but what we're gonna do is actually we're gonna attack this carbon over here, and this bond will go up to the oxygen, giving us this weird product. Looks like this, SOCl, right? And then now this is completely nice, and this is completely, this is what we're doing here is we're actually making this a good leaving group. This SO2, we were making it a good leaving group. So what's actually gonna happen is the lone pairs on this hydroxyl will come and form a double bond here. This C to O bond will leave and go up to this S to O bond. And then as that happens, this chlorine will leave. So what that forms is now this compound, right? And then if you can see now, this sulfur has this double bonded O, and then now this double bonded O as well. So we actually form an SO2 compound here. And this is a good leaving group because there's a lot of resonance, as you can see here, okay? And then this is just a basic deprotonation step that you can either do, sorry, the positives on the oxygen. You can either do it with the chlorine that just, this chlorine here that just left, right? Forming HCl, or you can do it intramolecularly if you wanted to, if it permits on the test, or if you just wanted to do it for practice. But in the end, you are going to get this acyl chloride here, as well as SO2, and then HCl is the more correct compound, right? Because then the Cl that just left over here can come deprotonate this H, giving back our double bond, and then now our Cl. Now we just made our acyl chloride, right? So again, why couldn't we use a simple reaction with this chlorine? Not only is chlorine a better leaving group than the hydroxyl, but also chlorine can be a good base. So what's stopping it from grabbing this H, right? And actually, we see this reaction happening. This can happen where the double bond here kicks off this hydroxyl, but it's just the equilibrium will be so drawn to the reverse reaction that we don't really use this type of reaction in a lab or in any setting, right? Instead, we use a thionyl chloride, this SOCl2 compound, right? And then the double bond, the carbonyl oxygen will attack it. We get this weird looking tetrahedral intermediate, right? This S is a tetrahedral. And then we get a chlorine leaving group here, which will then attack this carbon because there's a positive charge on this carbon if you do resonance. And then a lot of electron rearrangements. We get an SO2 and then a our acyl chloride, right? And then now we can do some reactions with this. So if you notice, the first thing you should notice about this acyl chloride is this carbon over here, this carbonyl carbon, right? We know from previous chapters that there's a chapter on carbonyls where we focused on how reactive this carbon was, right? There's a delta positive here and a delta minus, which gave it a lot of the characteristics that we know and love. But now we have a different substituent other than a hydrogen and a methyl group. In this case, we have a chlorine, which is very electronegative, which means it's this C to Cl bond is not going to be shared equally, right? It's going to go to the chlorine, which means this carbon here, not only is it already getting the delta positive from this oxygen, but it's also getting the delta positive from this chlorine. So there's a really, really big delta positive on that carbon, right? Which means if we react it with water, we don't really need um, a catalyst, right? Because it's really, really stable. And because it's really stable, we don't need a catalyst because this is really reactive already, right? So that means this oxygen can just attack this carbon here, and then we can just do this simple reaction where we have this water, right? And then again, as you all know, chlorine is an amazing leaving group, right? Chlorine is an amazing leaving group, which means this is a positive over here, negative over here. The double bond will go and the chlorine will leave as a leaving group. And now you can see where I'm going with this reaction. This O is still positively charged, but we just have the chlorine that left, which means it's going to come deprotonate this. Or again, you can transfer it intermolecularly, it doesn't matter. But as for the sake of correctness, it's a lot better to put it as the chlorine taking it. We just form a carboxylic acid, right? And we also get a HCl in the process of doing that. Again, this comes from the fact that this carbon here is really, really reactive because it's being pulled by not only the chlorine, but also by the oxygen, right? So that means the electrons, the sharing of this electron here is not as equal, which means we can do this without needing a catalyst. We didn't need a catalyst of anything, right? So that's why this can happen. This is one of the most basic reactions of acyl chlorides. And following that same mindset, we can then start to create other carboxylic acid derivatives, right? If you remember from our here, we have an amide, an ester, and an anhydride. And actually, you can make all these compounds here by reacting it with the acyl chloride because this carbon is so reactive, right? And first, we're going to focus on ester. This is one of my favorite compounds because I think it looks like a funny looking face, this ester. So two ways you can go about this. You can either use a base or acid catalyst. The book uses a base catalyst, or if you really think about it, even though methanol is not really a good, it's not really a good nucleophile, the fact that this is so reactive makes we're able to now do this reaction without needing a catalyst, right? So again, I'm not going to use a catalyst here, but you can if you want to. It'll just be the same steps. If it's an acid catalyst, then this oxygen will take the acid. If it's a base catalyst, the base will take this acidic H, making it more reactive, right? So now I'm just going to do this simple reaction here. Okay, and then we have Cl, O, OH. Again, Cl is a good leaving group. This O is a positive. It can go here and then it can leave. And then we get this. Again, a positive oxygen, which can then be deprotonated by either intramolecular or by this chlorine, which is the more quote unquote correct option. If that happens, we then get our ester, right? This cute looking face thing. And of course, you can vary the ester length, right? Let's say I wanted an ester that was 3 carbons long, 1, 2, 3. You don't have to just react it with this methanol. You can react it now with propanol or butanol or any pentanol, however many carbons this is, right? There's a lot of creativity that you can go along with it, and it leads you to a lot of options, which I really enjoy about organic, right? So that's ester synthesis. And of course, we can keep going with amide synthesis, right? I'm sure you all can see where this reaction is going to. Again, we don't need a catalyst over here because it's really reactive. I'm sure it's getting really boring now. I'm getting really tedious, but it's going to be the same reaction. Again, pattern recognition, right? This has a lone pair. It can come attack here, form this. Okay, it's getting boring now. This H, and then the Cl. The Cl will leave, right? And then you form this again, and then this nitrogen is a positive. You just keep going through this whole entire cycle of you end up getting something like that, and HCl again. Again, really, really simple. It's all about pattern recognition. I understand that it may not be this simple during tests or midterms, but if you follow the same mindset of, let me find an electrophile, let me find a potential nucleophile, right? Let me see what derivative I'm dealing with, you're able to solve these problems without a question or doubt, right? And when in doubt, always try. You never know what can happen, right? So again, we synthesize amides from acyl chlorides. And then our last one is the next, we're done with acyl chlorides. Now we're gonna focus on acid anhydrides, which I I I'm not really a big fan of anhydrides just because I think they look really weird. They look really scary to me. But again, don't be alarmed. I know that was like a really bad introduction to anhydrides. But so first, let's see what we have here. We have a carboxylic acid reacting with another carboxylic acid, right? We have heat and this P2O5 thing, which you don't need to know. The most important thing here is the heat, right? So this, I should add that this is anhydride synthesis, right? Not anhydride reactions. So what this heat does, you've seen it in a lot of reactions, heat. It's actually being used as a reactant. This is actually one of our reactants. What this means is we're gonna dehydrate this product here. And as you know now from a lot of organic chemistry reactions, when you're dehydrating something, you're taking out the water, right? But you're like, there is no water in this compound. But there actually is. You can see this OH over here, and one of the H's here. If we have two H's and an O, that's pretty much a water, right? So that's pretty much what this reaction is. You don't need to know the mechanism for this, as it is a really interesting mechanism with this phosphorus moiety there. But you're pretty much going to take out an oxygen, a water, and then combine the two carboxylic acids together, right? So it's gonna look like this, your N compound alongside the water. And you can sort of see how that's happening. You just take away this OH and then take away this H, connect the two together, you have your anhydride, right? Again, not really that, it's not really that hard, but it can get really tricky. Sometimes I'll show you like a very common example. You'll have something like this, right? Where now you have two cyclic anhydrides or two cyclic carboxylic acids. And again, you can do the same reaction here with heat P2O5, and you can get this reaction here. Again, you're just taking away these two H's over here, these two H's, you're putting the O's together and you're keeping everything the same, right? It does look different than what we did up here, but it's the same concept, right? And lastly, what we're gonna do now is we're gonna make these anhydrides using our beloved acyl chloride compound. In this case, we do need a catalyst. In this case, we're going to use a base catalyst, which is going to pull off this acidic H from this oxygen. So as it does that, it goes here, Cl, oxygen. Again, there is resonance here. I suggest you draw it out, but for the sake of time and sanity, I will just delete that. I'm not going to do the resonance. It's going to react there because, again, this carbon is a delta positive, right? As it does that, I'm going to put the Cl on the bottom there, not changing anything, just so you all can see it a little bit clearer now what I'm about to do. Goes here, takes the Cl, we just form our anhydride, again, from acid chloride. It's the same reaction, same type of mechanism, just doing it differently. And also, you're not wrong by not using any catalyst here because, again, this chloride is really, really reactive. I'm just using an acid or a base catalyst here just because to make sure that the reaction proceeds in the way that I want it to, right? But you're not wrong. You could also receive back an HCl if you did it with without the base, right? Because as you can see, this one would have the H, it would be a positive, and then the chlorine would just grab the H over here and go up to make this compound, right? Again, I hope this was able to help. Don't worry too much. In the next video, we're gonna cover esters, which again are my favorite, and then amides, which are the least reactive, but they're also really important, okay? I hope everyone has a good day and good luck on quizzes or midterms that you may have.